Hello, everyone, and welcome to part 2 of lecture 3 of Galaxies at Stockholm University. This one is the second half of part 1 of the lecture. The first part was about the spectral energy distribution. This second part is about galaxy spectra. The last part is going to be about the statistical distribution of quantities such as size, luminosity, and colors in galaxies. That is going to be the third video in today's series. But let's dive into our galaxy spectra. Looking at an SED as we did before, we can see that it is basically a very, very low resolution spectrum. It means that you see basically the overall very smoothed out shape of the continuum. You generally do not see spectral line emission in the spectral energy distribution. However, if the lines are very strong or very broad, they might still show up. The criterion is basically this. Remember that the spectral energy distribution is taken in a number of filters or band passes across the electromagnetic spectrum. And so if the line, a narrow line, is strong enough that its integrated area under this line can compete with the integrated continuum across the entire width of the filter or the bandpass you are looking at, then this emission line will actually affect the measured brightness or magnitude in this filter, and it will show up in the SED. This is the case when we look, for example, at very strongly star-forming galaxies, where we are often forced to take line emission into account when we are trying to model the spectral energy distribution that we observe from such galaxies. However, in quiescent galaxies, in early type galaxies, and in only moderately star-forming galaxies, this is usually not the case. The contribution from nebular emission in the ISM is usually not strong enough to affect the SED of this galaxy as we observe it. Sudden shifts in the continuum can happen, as we can see in the plot in the figure here. We can see that there are these places, for example, here around 4,000 angstrom, and another one out around here. You can see in some of these around like on the upside of 3,000 angstroms. The one at 4,000 angstrom is called the 4,000 angstrom break because astronomers are fantastic when it comes to naming things. We call these things here breaks or jumps or just discontinuities. Basically, a discontinuity is the collection of breaks and jumps. And we call it, by convention, we call it a break, as here, where it is fainter on the blue lower wavelength or smaller wavelength side and stronger on the red higher wavelength side. But that's just a convention. And by convention, when it's the opposite way around, we call it a jump. So there is the 4,000 angstrom break, which is often observed in early type galaxies. It can also be observed in some star-forming galaxies, but it's usually way less pronounced. And in very strongly star-forming galaxies, it is not observed. On the other hand, there is also the Balmer break that we observe at 3,646 angstroms. That is about here-ish. And that one can, on the other hand, be quite strong in star-forming galaxies, but is usually not super strong in early type galaxies. Interestingly, though, in star-forming galaxies, the Balmer break can become a Balmer jump if the ionizing radiation is strong enough from the stars in it to ionize the interstellar gas strongly enough. Then the continuum emission from this gas can actually become so strong that it will lead to a jump rather than a break around the Balmer lines, or the Balmer limit. This is something we will look a little bit more into at a later point. I just realized you could not see the last part here, but we have the 4000 angstrom break, as I said, and the Balmer break. Looking at spectral lines, the strength of a spectral line we measure as its equivalent width, as it is called. The mathematical expression for the equivalent width can be found here. But the intuitive explanation is that we take the integrated flux between the line and the continuum, this area, and then we ask ourselves if we instead had a rectangle that went from the continuum and down to 0 and had the same area as the integrated area here between the line and the continuum, how wide would this rectangle then be? So here is the line, here is the continuum. If we have the area between the continuum and the line, and we construct a rectangle of the same area that goes from the continuum and down to 0, that is its height, then how wide would that line be? And that is called the equivalent width of the spectral line. We can do this both for emission and for absorption lines. By convention, which again can be a little bit confusing and counterintuitive, for absorption lines, the equivalent width is positive, whereas for emission lines, the equivalent width is negative. But in practice, we always know whether we're working with equivalent or with absorption or emission lines, and the sign is often omitted. Another important way to describe a spectral line is its full width of half maximum, as we can see here. If we look over at the line from before, it is basically where you take the value that is at its half maximum, so halfway between the continuum and the peak of the line, to find the half midway point between those two. And then you measure how wide the line is at that value. That is called the full width of half maximum. You can have lines that are very broad and very shallow, and you can have lines that are quite deep but quite narrow. And these can have the same equivalent width, but very, very different full width at half maximum. The broadening of these lines, especially when we talk about emission lines, is caused by the velocity distribution of the atoms in the gas that do the emission or the absorption. Which means that if all the gas was completely static, and if all the atoms in the gas were completely static, then of course absorption or emission would happen at only one wavelength, right? And your line profile would be a delta function. But because there is a velocity distribution inside the gas, that also means that there is a distribution of wavelengths at which the emission or the absorption happens. And typically in a normal thermal gas, this velocity distribution is a simple normal or Gaussian distribution, and therefore the emission or the